couple of things I need to point out. I did move the lab for next time to next week, which means it puts it on next term. So the lab we were going to do next time, I've moved to next week, the endothermic exothermic. So that means after we do the little lab today, that's a 15-minute lab, you can finish your lab notebooks and get them in. We're going to get through most of the notes today except for one page. We'll finish that on Friday. And Friday will be clean up everything, work on sapling, get whatever you need to get done. Remember, you need to have sapling up through 6.4 done. And the quizzes up through 6.4 done for Friday for the term grades. Then next week we'll do the endo-exothermic with heat curves, and the week after that we'll do the specific heat lab. The test is open for this unit from January 18th through the 24th, so make sure you've got some time that you can take in. Also, I have reopened the family quiz and given you 60 minutes to do it. Till Friday at 11:30. Okay? If you want to retake it, great. If you don't want to retake it, that's fine. But I did give you a little bit more time, and I've checked some of the questions you guys were questioning. Also, I do have extra credit paper towels that I'm offering that you can do it. Basically, it's an extra credit quiz, which is 10 points. Quizzes are more than assignments, so it actually is weighted pretty good. So if you had some quizzes that you just couldn't get up to that 10 points, or at the very beginning you missed some points, some way to get it back. Friday. Yes. So so it goes into your quiz bank area. So it goes into quizzes. So it'll cover. It just goes into the bank because it rolls over and rolls over and rolls over. There's a bank that's just quizzes, so it'll add 10 points in. So 10 points that you might have lost somewhere, you're going to gain it back. Okay? All right. Let's go ahead, get your notes out. Let's get these notes taken so we can go on. I'm going to do a real quick review before we get started. We started with gas laws. Last time we had some labs that we did with gas laws. Tell me, what is the ideal gas law?
Oh, wait, toddler rules.
No, it is toddler rules, but what is the actual law? The actual law. Ideally, you're not a perv nerd. PV equals nRT. Okay? Okay, so I reviewed toddlers last time. Okay, second one. What is the combined gas law? That was solving perv nerd for R and then setting two equal to each other. So what was that law? P1V1 divided by T1 equals P2V2 divided by T2. Okay? Remember, the N's sort of dropped out. They could be there, but they were probably not. Then we talked about Boyle's law. What was held constant in Boyle's law? Temperature. So the law for Boyle's was what?
P1V1 equals P2V2.
Good. P1V1 equals P2V2. Then we got to Charles' law. Prince Charles. What was held constant? Pressure. And so its law was what?
V1 over T1 equals T2.
V2 over T2. So V1 divided by T1 equals V2 divided by T2. Then we got to Gay-Lussac's law. What was held constant? Volume, because we're sucking through a straw. That's volume. Okay, and what was its law? P1 over T1, P2 over T2. Good. Okay, then that was all the laws that had to do with the ideal gas law. Then we shifted and we got Graham's law. And I told you I remembered it by grandma. What was that law?
Oh,
we did it with the straws last time.
the
Rate of A divided by rate of B equals square root mass of B divided by mass of A. Okay, and then we had Dalton's law. Then we had Dalton's law. What was Dalton's law? That was a duh law.
Oh, the combined pressures of something is the total combined.
Yeah. The total pressures equaled all the little parts of pressures that you have. We used it in the last lab by Y. Why do we usually use it in lab?
Wait, what?
Dalton's law. because we collect gases through water. Okay, guys, we're going to put the phones away, or I'm going to take them. Evidently, you can't handle it. So put the phones away. Okay, I'm usually pretty lax with that, but if you're not paying attention, not going to happen. Okay, second thing. This law right here actually has to do with the pervnert. He worked with volume and moles directly. So what did he hold constant? Think back to the combined gas law. What did he hold constant if he worked? Temperature and pressure. He held both of those constant. So what was his law look like if we were to draw an actual formula for his law, for Avogadro's? V1 over N1 equals V2 over N2. Okay, so his law would be a little bit different. They're directly related. Okay, number of moles went up, the volume went up, because they had to equal the same thing. Okay, so as we're looking at this, you could take a mole of anything at the same pressure, at the same temperature, and it would be exactly 22.4 liters. Okay, we have now added that to our mole map. We can now go from moles to volume. Okay, now we're going to do a whole bunch of practice problems, and we don't know which of these laws we're going to be using, so we're going to have to pull stuff out as we do it. So let's go ahead and pull stuff out. Pressure, the pressure. I'm looking, I don't know what the pressure is. There's no pressure there, so that's a question mark. And it's the first one I come to, so I'm going to put P1. By 2.0 mole. Ooh. N is equal to 2.00 mole of oxygen confined to a volume of 500 milliliters at a temperature of 20 degrees C. Oh, what did I have to do always with temperature?
Kelvin.
Put it into Kelvin. So add 273.15 gives me 293.15 K. Ooh, all right. What law am I going to be using? The ideal gas law, which is PV equals nRT. And I'm solving for P, right? So I'm going to divide both sides by V. And I'm going to get P is equal to nRT divided by V. What was R? 0.821 atmospheres times liters divided by moles times Kelvin. You use it a lot. Okay, so now just plugging in for everything we've got. Pressure is equal to the moles, 2.00 moles, times R, 0.0821 atmospheres times liters divided by mole, times Kelvin, times by temperature, 293.15 K, divided by volume, 500. Ooh, good catch. It's not in liters. So we got to change that up here to liters because it's not in the right unit. So there's 1,000 milliliters in 1 liter. So that means 0.500 liters. 0.500 liters. Now, before I plug it in my calculator, I do a check to make sure everything unit-wise cancels out because I would have caught that, but he did first. So mole cancels with mole. Kelvin cancels with Kelvin. Liter cancels with liter. And I'm left with atmospheres. And pressure is measured in atmospheres, so I'm okay. I can plug that through my calculator now and get an answer.
Wait, how'd you get the ratio?
How'd I get what ratio?
The zero.
The constant, that is just always there. I've got to have it memorized or put it on my 3x5 card. Okay? All right, what do we get for an atmospheres? Three sig figs. Who's got an answer? 96.3, which would crush our bodies immensely into mush. Do we have a second? Yes. Okay, because I had only one pressure, only one volume, and only one temperature. And all the other laws, I need 2 of something, right? Good question. Okay, going forward, let's do this. A volume of hydrogen gas in a still container. So I have hydrogen gas. I don't know if I need that later. A still container takes that many moles, so N is equal to 0.525 moles of the gas, exerts a pressure of 3.00 atmospheres at a temperature of 10 degrees Celsius, and I've programmed myself to make sure to change it right now to Kelvin because then I don't mess up. Okay. Oh, it looks like, what are we looking for? We're looking for volume. Oh, this is going to be what law? Ideal gas law again. PV equals nRT. So I'm going to need R, 0.0821 atmospheres times liters is a constant, mole times Kelvin. So double checking, making sure I've got everything in the right units. Atmospheres, yes. Liters, I don't have. I'm trying to solve. Moles, I've got. Kelvin, I've got. Okay, so I'm looking for volume this time, which is right here. So I'm going to divide both sides by pressure. So volume is going to equal nRT divided by P, plugging in 0.525 moles times 0.0821 atmospheres times liters divided by mole times Kelvin. Then we also have T, which is 283.15 Kelvin, divided by pressure, which is 3.00 atmospheres. So canceling out units, double checking myself. Moles goes out, Kelvins goes out, atmospheres goes out. Volume is indeed in liters. So what do I get for my unit, for my number? 4.07. Do I have a second on that? Okay, going forward. Sorry. Okay, temperature in Celsius. I'm looking for temperature, but I need to make sure to convert it to Celsius at the end. Because I know in the gas laws they all have to be in Kelvin when I'm doing calculations. So don't let this mess you up by trying, oh, I'll just do it in Celsius. Remember, when we do calculations, it has to be in Kelvin. So, of nitrogen gas has a volume, 2.50 liters, and a pressure, 300 point torr, and contains 0.100 moles. What law? Ideal again. So we're stuck in the ideal for a minute. PV equals nRT. What are we looking for this time? Temperature. So this time we're going to divide both sides by nR. So I'm going to put R here again, 0.0821 atmospheres times liters divided by mole times Kelvin. And we've got temperature equal to PV divided by nR. Can I leave it in torr?
Oh, yeah.
I've got to change it to atmospheres. So how do I change it to atmospheres? 760, whoops, sorry. Let's try that again. 760 torr for every 1 atmosphere. Torr goes out, and 0.395 ATM. Okay, is there anything else that we need to change? Okay, so let's put it through. Pressure. Try that again. 0.395 ATM times by volume, 2.50 liters, divided by N, which is 0.100 moles, times by R, 0.0821 atmospheres times liters divided by mole times Kelvin. Again, take a minute before you actually put in the calculator, make sure the units cancel. Mole cancels with mole, ATM with ATM, liters with liters. we've got 1 over K, which is Kelvin. I'm going to put it up here. Don't forget when you have more than one thing on the bottom to make sure when you hit divide you do a parenthesis and a parenthesis at the end so you get the right answer. Either that or do like we had to before, times the bottom together, then do 1 over x and then times through the top. That works too.
Why do you have to?
Because if you don't, what happens is it'll divide by the 0.1 and then it'll times the whole thing by 0.0821. And you'll get a wrong answer. Okay, has anybody got an answer for temperature in Kelvin? Okay, 120.3. Does anybody have a second on that one? Second that. Awesome. How do I get it out of Kelvin? They wanted it in Celsius. Minus 273.15. Okay, what do we get? We get a minus what? 152.9. Okay. That is cold. That is cold. Okay. I'm pausing. While I'm pausing, I'll stretch this muscle. Back is sciatic is out. Yes. Torr is millimeters mercury, and Torr was the guy that invented that measure of pressure. So they call it torr or millimeters mercury. It's the same. Okay. Okay, we okay to move forward, Mason? You already answered. Okay. Yes. Right here? Right here? You'll multiply these two, then hit your divide, parentheses, multiply these two, close parentheses, and enter. Okay? All right, we all okay to move forward? All right, so now we're going to go a little bit more. Okay, here this time we have mass given to us. So 2.00 grams. I don't know what to do with that right now, so I'm not going to label it. I'm just going to put it out, pull it out. Of a gas that has a volume of 1.12 liters at STP. What does STP mean? What's standard temperature? Kelvin what? What number?
Oh,
273.15 Kelvin. What's standard pressure? 1.00 atmospheres. Calculate the molecular weight. Ooh, molecular weight, remember, is grams per mole. That's how many grams there are per mole, right? And then identify which one of the gases I've got. Okay, whose law am I going to use? This is still the ideal gas law because PV equals nRT. This is moles, right? So if I can find moles and I've got grams, I can take grams divided by moles to get the molecular mass.
Yeah, but we don't know what.
We will. Okay, so we've got R. 821. I'm sorry. Yep, it's always the same. R is always the same. It is a constant. That we're looking for N. So we're solving for N, so we're going to divide both sides by RT. Okay, so N equals PV divided by RT. Pressure, 1 atmosphere, times by volume, 1.12 liters, divided by R, 0.0821 atmospheres times liters divided by mole times Kelvin, times by standard temperature and pressure. And temperature of 273.15 Kelvin. So we're going to do 3 sig figs. Kelvin goes out, liters go out, atmospheres go out. It's 1 over mole, which is a mole. So I'm going to go N equals something mole. So let's get 3 sig figs on that. So remember on the bottom here, you can times to the top, divide, parentheses, times to the bottom, close parentheses, and hit your equal.
Does it have to be
It can be really close.
Or is it 0.01?
0.0. Give me 3 significant. These don't count. 0.500. These 2 don't count. Those first 2 don't count. So if I need 3 significants, I need these back here. Okay, so to get the molecular weight, I'm going to take 2.00 grams divided by this moles, and you should end up with about 40. Well, if I look at each of this one's 4, this one is 20, and this one is 39.9, which is basically 40, so I would say it's argon. Okay? This is a common problem. You probably will see it again. Okay? So make sure you can know how to do that. Even though we didn't have what it looked like at first, it was like, oh, I don't know how to do that. Remember, molecular weight is grams divided by moles. Okay?
I did tackling 6 yesterday and I had Avogadro's law and I had to figure it out because I was like, because then I ended up figuring it out, but it was so confusing.
Yes.
What law do I use?
Yes. So I look at my laws, and so that's something I would have on my 3x5 card when I went to do the test, is my laws, and I look and see what I'm given and what I need, what law fits all of that. So most of the laws need 2 of something, like 2 volumes or 2 pressures or 2 something. So if it's just 1, then I know, oh, it's got to be ideal, because it just has 1 of each of them. Okay? No, we're going to be working with more. Okay, we ready to move forward? Yes.
Sorry, do we have all that?
Yeah.
Sort of, not really.
If you don't use them, are they extra credit?
No. You have grace cards, that's extra credit if you don't use them. Okay? Okay, we're going forward here. So, make sure I didn't just skip what we needed. Yes. Okay, a still container. And I've told you several times I'm a very visual learner. So we need to make sure we do visually. Still container contains a mixture. So here's my still container. I am not an artist. I just do something real quick. It contains nitrogen and oxygen and carbon dioxide. The total pressure in the tank, PT, is equal to this. The pressure exerted by nitrogen is 810 torr. The pressure exerted by oxygen is 920 torr. And it wants to know what the partial pressure of carbon dioxide is. And that's how you would write the pressures. If you're looking at a specific pressure, you do a subscript of what it is. Okay? Whose law?
No.
Duh, this is the duh law, which is pressure total is equal to all the pressure added up, right? Da-da-da-da. Okay, so we're going to have pressure total here is going to be equal to pressure of nitrogen gas plus the pressure of oxygen gas plus the pressure of CO2. Well, if I'm looking for CO2, I'm going to subtract the others, so pressure of CO2 is going to equal the pressure total minus pressure of nitrogen minus the pressure of oxygen. Is everybody okay with that? Okay, then you just plug the numbers in. So 2,100 torr minus 800 torr minus 920 torr, running out of room. Okay, so pressure of CO2 is going to be what? Yes? Okay, they become minuses because I've got to get them off this side. So to get them off this side, I subtract P nitrogen from both sides, subtract oxygen from both sides. If you have to just put the numbers in as they are and then move them over, that's fine too. Okay? It's just how do you math? As long as you math and it's right, you're okay. Okay, we okay? Move forward? Okay now? You're not even doing anything. Just saying no. Honestly. Okay, so let's look at the next one. We have, here's a volume of 250 milliliters of a gas. I'll call it volume 1. Collected by water displacement. Okay, so I've bubbled the gas or something, and I've collected some gas up here. And it's oxygen, but it also has water in it. Okay, so I've got these two things in them. Okay, the partial pressure of the water vapor, so pH2O, is 22 torr. Calculate the partial pressure of the oxygen if the total pressure is 720 torr. Okay, how do I do this? We did it in lab last time. Yes?
Does the volume even matter?
Good question. Does the volume even matter? I need to know. No. I pulled it out, but this doesn't matter, right? I pull out what I need, what I think I need, and then at the very end I go, okay, do I really need it? No. Okay? Because I might need it, and if I didn't pull it out, then I messed up. Okay, so remember pressure total is going to equal pressure of the oxygen plus pressure of the water, right? So pressure of the oxygen is going to equal pressure total minus the pressure of the water. So 720 torr minus 22 torr gives me 698 torr. Good. Yeah, it's just a little short. It's a short one. It takes 10, 15 minutes. Okay, we ready? Okay, back row, I'm about ready to slam dunk you. Stay with me. Okay? Yep, you did. I didn't say how I was going to slam dunk them. I might just slam dunk the grade to F. Okay, next up. Okay, the mass of bromine molecule. So bromine molecule is 160 U. And the mass of argon is 40 U. Compare the rates at which these gases will diffuse. So anytime it says rate, right away I go right to Graham's law because it's all about how fast things move. Well, Graham's law was what?
Rate 1 over rate, or rate 8 over rate B. So that's Is it nice? Oh, yeah.
So it does switch. So B becomes on the top over here underneath the square root. Now, when it says compare the rates, this right here is also referred to as relative rates. Okay, so that whole fraction or that whole number on that side is considered relative rate. So we've got two things. Whenever you're reading a problem, the first thing that you come to is always going to be A. The second thing you come to is going to be B. So that's how they're, yes, because that's how they want you to report it.
So whichever one comes first.
That's A. So as I'm doing this, the relative rate here is going to be the square root of argon, which is 40U, divided by bromine, which is 160U. Okay, the U's cancel. So I'm going to do the square root of 1/4, right? Which is what? Because 40 will go into 164 times.
Wait, why'd you wait? Oh, yeah. Oh, the square. Okay, so I was right. Okay.
You can put it in the numbers. I just simplified it down.
I put the 1/4 and then I saw it right. Okay, that makes sense.
Wait, why does 40 go on
Because 0.25 times.
Why does the 40 go on top? Because if you'll notice here, B is on the bottom here, but on top here. So when I'm using mass, it goes on top. There's no unit because the units would cancel each other, right?
Oh, that's just the rate, so
It's just a relative rate. It's how fast compared to this one.
so then
Yes.
it's the rate times.
So because this number is smaller, what does that tell me about the relative rate? That tells me B is a lot faster, got a higher number than A. So B is faster, which makes sense because it's a less weight. So argon is faster than bromine. Okay, yes.
So how would you know that it's talking about argon? Like, obviously we can see that it's the lighter element, but like with the 0.5, how would you correlate that to mean that it's faster?
Because it's basically saying the rate of bromine compared to the rate of argon is equal to 0.5. If it's less than 1, then the bottom one's going faster, a bigger number, right?
So bromine is half the speed of argon.
Right.
Okay.
But
Right.
what factors like what
You all, whatever you come to first becomes A. Whatever you come to second is B. Yep. Okay, going on. Now you got to think, they didn't give me any numbers this time. Which will diffuse faster, the HE molecule or the NE molecule? Why?
Because lighter.
Okay, if I didn't know and I needed to convert, I could say this is about a 4, this one's about a 20, and I could put it in. This would be A, this would be B. So B goes on top, 20 divided by 4, and that would be square root of 5, which would be 2.25, which means A is moving a lot faster. Right. So helium is 2.25 times faster than neon. Okay? Does that make sense? Neon, helium is going faster. Because if you look at this, this would be rate of helium divided by the rate of neon.
But isn't it because it's the lighter one?
Right. B goes on top when we're doing math, remember? Rate A divided by rate B is equal to square root of the mass of B divided by the mass of A. They switch places. Helium is faster by 2.5. 2.25. Okay, so now I've got a riddle for you. Nope, it's not the end of the notes.
Yay! I like riddles.
I need 2 people. And since my back row is having problems, I need 2 of you on the back row come up. Hey, will you hold this for a minute for me? Just busted that. No.
Did you really say? She goes hope squad, and I was like,
Oh, really?
this is going really well.
Yes, it is. Very, very well.
Maybe just make it a lot bigger.
Oh, sorry.
It's all right. Okay. Now, each of you take one. Which one do you want? Top, big one or little? Okay, so here's the riddle. We've got one that is not blown up all the way. We've got one that's pretty blown up. Okay? These valves right here are closed, so you're going to actually have to hold those, make sure they don't come off right there. Okay, I'm going to open the valves, and I'm going to have them play with the balloon with their other hand to move the air back and forth. Is the little one going to get smaller or bigger? Is the big one going to get bigger or smaller? So read these, A, B, and C. You're going to hold up this if you think it's A, B is this, and C is this. A, B, or C. Make a decision. A, B, or C. Okay, you got it? Okay, ready? I'm going to open it up and let's see what happens. Ready? You're going to play with your balloon. Okay, play. Squish, 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 squish. Come on.
I'm doing
Come
it.
on.
I'm going.
What's happening, guys? What's happening?
Oh. This one? I don't know.
Oh, this one's getting.
This one's getting smaller.
What's
It's like,
happening?
oh, it's taking the air from.
It's taking the air from this one. Does that make sense? This one's actually getting smaller. She's got like nothing there. Okay, what do you think?
Like,
Because the balloon is already kind of spread, so it's just more willing to take in more air. I don't know.
It's like breathing over here. Okay, thanks guys. I'm going to let you go ahead and sit down. So even if I leave this open after they finish, look what's happened. Okay, why would this happen? Why didn't it equalize out? Like you guys said.
Because the rubber in the purple balloon is going to, like, it's already spread way far, so it's just more willing to spread further, I guess. I don't know.
You ever blown up a balloon? When's it hardest to blow up the balloon? Very beginning, because the pressure of the latex is pushing down, right? It has big pressure. Once it's spread out a little bit, it's pretty easy to blow it up, right? So we're going to talk about the pressures in the balloons. Okay? Mm-hmm. Okay, so we have pressure that is exerted inside and outside the balloon. When we go to blow up a balloon, stay with me guys. When we go to blow up a balloon, we have to put more pressure on the inside to make the balloon expand out. Okay? When the balloon is filled and we tie it, we actually have equal pressure. So when we were doing our lab yesterday and we had to move the burette from the ice cream bucket to the tall graduated cylinder, we had to equalize the water inside and out. We were making the pressure inside and outside equal, okay? Because at the point where it was hanging up there, it was not equal. They actually had a vacuum going. Okay, when we deflate the balloon, we have to have more pressure on the outside of the balloon than there is on the inside. And that happened a couple times when I was trying to attach those balloons and they went flying. Okay, so now we're going to talk about changes of state. Those are the triangles down at the bottom. We actually have some things going on. If I'm adding heat, the red arrows is what I'm following. If I'm taking heat away, then I'm following the blue arrows. And I sort of covered the wrong ones because I moved it up, but that's okay. So we're going to talk about endo and exothermic processes. Most of you know about condensation and evaporation. Those are big, easy ones. We're going from a liquid to a gas to a liquid. You also know about melting and freezing, back and forth. The ones you probably don't know very much are sublimation and deposition. That is going directly from a solid to a gas, that's sublimation, and deposition is going from a gas to a solid. The best example I can give you is carbon dioxide. We take carbon dioxide from the air as a gas, and we take energy out of it, and it goes immediately to a solid as dry ice. As we leave dry ice out, dry ice will evaporate. It won't go into a puddle. It'll just evaporate and go away. So that is known as sublimation. So we need to be able to know those terms. So as I'm doing this, now think about, this is on the next page. We're going to think about endo and exothermic. So am I putting heat in or am I taking heat out of the situation? So condensation, going from a gas to a liquid. Exothermic, boiling something. I have to put energy in to boil it, right? Sublimation, going from a solid to a gas. Endo, so this is also in your notes. Okay, and D, liquefaction. That's going from a solid to a liquid. It should be it should be endo. Okay, freezing. Exothermic. Vaporization. That is endo. That D should be endo. Okay, so you should be able to look at anything I give you and tell me what's happening. Am I putting energy in or am I taking energy out? Okay, now going on here, when we talk about evaporation, we also talk about vapor pressure. As long as I have an open container, evaporation is just going to take place and eventually my water level is going to go down, right? If I have a closed container, have you ever made terrariums and you only have to put like a tablespoon of water in and things keep growing? It's because it has a cycle. Some of it goes up to gas and then it comes back down as water, and it goes up to gas and it comes back down as water. Same thing happens when we have vapor pressure. So some of the gas gets vaporized or put into gas, and then it loses its energy and falls back down as liquid. So that pressure that builds up becomes an equilibrium. We call it vapor pressure, and we're going to be working with that later. So I'm going to give you a lot of verbiage stuff right now. So evaporation, we talked about that already. It's an endothermic process. You don't have to put everything down word for word, just have it explain it. Okay, it's going from a liquid to a gas. Evaporating molecules carry away with them kinetic energy. So what's left behind has a lower kinetic energy. What happens to the remaining liquid? It becomes cooler. The process above is called evaporation or vaporization. Condensation is an exothermic process in which gases lose energy and become a liquid, or a liquid loses energy and becomes a solid. Vapor pressure, we talked about that in the last slide, is a pressure exerted by the vapor or gas that is in an equilibrium with its liquid. So it has to be in a closed container. And then the last one here, what types of molecules tend to have higher vapor pressures, polar and nonpolar? This is with the kinetic law. It is nonpolar because they're easily able to come out of solution. They don't have the attraction or repulsion that keeps them together. And you don't have to have it word for word. So think toddler rules on the last one. Okay, nonpolar because they don't attract or repel. Okay, going forward. So as I'm looking, how many of you have ever put rubbing alcohol on your skin? Okay, what does your skin feel out after you've put it on? The same, warm, cooler, hotter? Usually colder. It'll evaporate out and give you a little bit of a cold feeling or sensation. So if you put different alcohols on the back of your hands and just let them evaporate, gasoline would be one of them that you could do, it would give you a different feeling. So if I put two different chemicals on the back of my hands, how would I know which one would give me the coldest feeling the fastest?
The one that evaporates slower.
He says slower, you say faster. Which one is it?
Wait, did John say faster? I don't even know what I said.
Think of Graham's law. Think of Graham's law. The one that's lighter, the one that moves faster, because it's going to take more energy with it. So, how do I know which one of these is going to move faster? Is it the left hand or is it the right hand? Or is the right hand or left hand? Okay, we said the blue. Why? It's lighter. It has 2 carbons versus 4 carbons, only 6 hydrogens versus 10 hydrogens. It's lighter. It's going to be moving faster. It's going to go to a gas faster. And because it goes to a gas faster, it's taking that energy with it and taking it away from you. So that feels cold. So when you have a cold pack, it's actually a reaction that takes energy from you. That's why it feels cold. Okay? If you have a hot pack, that's actually a reaction that's giving off heat rather than taking it in. Okay, so let's go forward here and do a couple more definitions. So sublimation is basically where you go from a solid to a gas. Do not go through the liquid phase. Okay, solid to a gas without becoming a liquid. Melting point, you guys should know this, it's where we change from a solid to a liquid. It's equal to the vapor pressure. And decomposition, we've talked about decomposition as far as equations, but decomposition can happen because of heating. So if decomposition happens because of heating, and that's what we're in right now is heating and gas laws, which is called thermochemistry. And 3 common substances that sublime. We talked about one already, it was carbon dioxide or dry ice. Another one is water. What? Water freeze-dried. So have you ever had, how many have the old-fashioned kind of ice cube makers that you put the water in, then you put it in the freezer? Ice trays, yeah. If you leave those there a long time, what happens to the ice?
Freezes.
expands?
It does. It does get smaller. So it freezes, but if you leave that ice in there too long and don't use it, and then you come back after a while, it's like it's shrunk down, and it's got sort of granularly, and it doesn't look the same, and it doesn't fill the ice cube tray like it did originally. Okay, and that's because some of it's gone straight to gas. It's sublimed in your freezer. As long as your freezer doesn't have any extra moisture in it, it'll sublime. Iodine is another one that goes straight from a solid purple crystal to a purple vapor, which is pretty cool to watch. I'll have to see if we still have some iodine in the back, and I'll show you. Okay? We okay to go forward? All right, so these next two graphs are often used on the ACT and the SAT, so you need to make sure you familiarize yourself with how to read these. This is known as a phase diagram. So there's a phase diagram for every single chemical and element that we have. Okay? A phase diagram tells me the phase. It's basically a roadmap of that chemical. So solids are always right next to the pressure line. Liquids or gases are always right next to the temperature line, and that Y in between is always your liquid. So each of the black lines becomes sort of a map for the changing point. The bottom one up to what we call the triple point is where I go from a solid to a gas, that's sublimation, or from a gas to a solid, which is deposition. This line right here is my boiling line. So it's where I'm vaporizing or condensing. The one that's going straight up between the solid and liquid is my melting, my freezing point line. This triple point right here, I can actually take ice water and boil it and get gas off at this point if I have the right pressure and temperature. It's one point in time though. Okay? Over here, this critical point, at that point the temperature is so high for this compound that it doesn't matter how much pressure I put down on it, I can't make a liquid anymore. Past that point, everything's gas. Okay? So it is a roadmap to the chemical. And you need to be able to, given any point of temperature and pressure, tell me if I'm right here as a liquid, or I'm right here, or what happens if I increase the pressure if I'm right here, or increase the temperature. Is there a phase change, and what temperature would that phase change happen? Okay, so you need to be able to look at the graph and be able to get information off of it for me. If I ask you what the critical temperature is, you come clear out here and come straight down. If I ask you what the triple point pressure is, you come here, kind of thing. Okay, so be able to read the graph. Questions? Or we got all this down? You okay to move forward? What? Equilibrium is when it's right. It's going back and forth between a solid and a liquid. That's that line. So basically, it's my melting point line. These right here. The critical point is past this point right here, going this way. I'm going to be gas. Doesn't matter how much pressure I put on it. It's just going to be gas. It's too excited. Okay, then we get to this graph. This is called the heat curve graph. This heat curve graph basically gives me a lot of information. We're going to put a lot of stuff on it. Hello? Anything that has a slope. So anything that has a slope is going to be heating a solid, liquid, or a gas. So the first slope area in the solid area is heating up my solid. When it starts to flatline, that's when I start changing from a solid to a liquid. That will be my melting point. Then in the yellow where I have a slope, again, that's heating the liquid up. When I flatline in the yellow, that's when I'm changing now from a liquid to a gas. When everything is turned to a gas, in the blue, I'm now heating the gas up. So this top one in the liquid is my boiling temperature. Okay, so you need to be able to identify what's going on. So from this graph, without knowing anything else, I could get the boiling temperature for this compound and the freezing point of this compound. Okay, but there's other things we can actually gain from this. So you're going to see the same graph in the next one with a few more things to it. This equation, okay, in the red right here, anything in the red is going to have this same basic equation. This basic equation is called the specific heat equation. Okay, And we use it when we're changing temperatures. So M represents a mass. C, I call it CP, you'll hear me call it CP. That's a specific heat for that phase. So you not only have a specific heat for a compound, but it's for the phase. So the specific heat for ice, solid, is different than specific heat for water, liquid, which is different than specific heat for water as steam. Okay? Then change in temperature is how do I change in temperature? Okay? When we get a flat line, we can't use that equation. We can't use a specific heat equation because there's no change in temperature. So we move to what's known as heat of fusion, which has to do with fusing or solids, times the mass, or heat of vaporization, how much energy it takes to vaporize something, change it into gas, times its mass. So we're going to be using, we're actually going to go into these more next week when we actually do the labs that have to do with this. But these are equations that we're going to be using a lot. Okay? Yes? Okay. So, looking again, ice, water, heating the water, water and steam, steam. Okay? All right, now what we're going to do is I'm going to explain the lab that we're going to do, because we're going to stop here. That's the bottom of that page. And we're going to go explain the lab. You should easily finish because fifth period had only 15 minutes and you guys have got closer to 20 and they finished. So let's go here. I'm going to explain it. I actually have set it in the lab for you because it got a little messy in here. This is what we're going to do. We're going to try and find the heat of fusion of ice. So we're going to find the point at which it goes, how much energy it takes to melt ice. Okay? So what we're going to do is you've got a graduated cylinder. Okay? They are 50 milliliters. So the first thing you need to do is find where it says 70 milliliters on yours and change it to 50. Okay? Of hot water. So you're going to put hot H2O into the graduated cylinder. This is what I would suggest you do. Make sure it's hot water. Fill it up, then fill it up again. Does it have to be exactly 50? No. If you end up with 49.5 milliliters, that's fine. Just write down what you have. The thing that you want to do, though, is you want to warm those graduated cylinders up. Because if you don't, they'll suck the heat away from your hot water before you work with it. Okay? So fill it full of hot water once, fill it full, dump it out, fill it full of hot water again, then quickly do your experiment. Okay? While somebody's doing this in your partnership, somebody else is getting a little beaker full of ice. Okay? Now, before either one of you get this done, you need to make sure you pick up a calculator, hook it to an easy data, hook it to the temperature easy link.
Not easy link.
Yeah, it's an easy link.
It was a joke.
Oh.
I mean, technically, it should come to you.
Yeah. Okay, so and you got a temperature probe. It should come up reading a temperature. If it doesn't, you have a problem. Okay, the battery's too low. Bring me that calculator. Okay, do not put it back in the bunch of calculators because then somebody else is going to get it and it's not going to work. Okay, so you need a temperature. Once you have a temperature here, you don't need to go into anything. You don't have to print anything out. You just want that temperature written down. Okay, you want this, whatever it is, written down. Okay, then you're also going to have a styrofoam cup. You're going to pour the hot water in. You're going to get the temperature probe. And you're going to get the temperature of the hot water. Okay? In Celsius. Write it down. Then you're going to dump your ice in, and you're going to stir. And it's going to take two of you. One stirring, one watching the thermometer. Because the minute the last ice goes away, you want that temperature. Okay? You don't want to keep watching it. You want that lowest temperature. Write it down. You're done with that. You clean it up. Okay? The second part you're not done with. You need to take this and put it back into here and measure how much volume you have. Now, I don't know how many times I answered this fifth period. Please don't make me answer this over and over again. Yes, you're going to have more than 50 milliliters, so pour in 50 milliliters, stop, dump that out, pour in the rest, add that to the 50 that you had originally. So it's going to be above 50. You should have more than 50 milliliters when you're done. Don't just keep pouring it in and it goes above the 50 and you can't read it. Okay? So stop at 50, bottom of the meniscus, dump it out, pour the rest of it in, add that to 50, put it on your chart. Okay? So there's 4 things that you need. Beginning temperature, end temperature, beginning volume, end volume. Once you've got that, clean up, I'll give you a stamp, you're done. Okay? You don't have to wear goggles, you don't have to wear aprons, you just go.